Hello class, today we're going to be talking about matrices, and matrices are basically collections of numbers in rows and columns. So if you don't remember, a column is vertical. So in this case, this matrix has 1, 2, 3, 4, 5 columns, and this matrix has 4 rows, 1, 2, 3, 4. So we call this matrix a 4 by 5 matrix because it has 4 rows and 5 columns. So let's take a look at our vocabulary. Again, a matrix is a rectangular arrangement of numbers in rows and columns. We call the dimensions of a matrix the number of rows and the number of columns. So we indicate that as m by n. So in our case, our example, it was a 4 by 5. So it was a 4 by 5 matrix. And we call them elements, or the numbers in the matrix, the element. Okay? And if you remember, we had various numbers. Okay? These are some other kind of definitions we're not going to really use as much, equal matrices, but they have the same number, the same dimensions, and the same elements in corresponding positions. And we'll talk about that a little bit later. Scalar is just a number, a number that you multiply by a matrix. And when we do operations of matrices, it's very easy because when you multiply a number by a matrix, all you're doing is you're multiplying each element in the matrix by that scalar number that you picked. We'll look at some examples. And then for adding and subtracting matrices, first of all, if you're going to add or subtract matrices, they have to have the same exact number of dimensions. In other words, they have to have the same number of rows and the same number of columns. If not, you can't add them or subtract the matrices. If they do have the same number of rows and the same number of columns, then you can add or subtract them. And how you do that is you take each value, corresponding value. So when we talked about corresponding, in correspondence, let me show you this one. So this is, I want the highlighter, sorry. A and E are the first element in the first row and the first column of both of the matrices. So to figure out the result of adding these two matrices in that first position is the sum of these two values. To figure out the next position, it doesn't matter which order you go into, as long as you place them in their corresponding position. We take B, which is the first element in the second column, of the other matrix, and add those together. And in corresponding, C and G correspond because they're the first element in the second row. Add them together. Vice versa for D and H, which are the last element in the last row. And we add them together. Super simple. Okay? We use the same coordination even though we're subtracting. Here, A minus E, so that means we're going to subtract E from A. B and F, we subtract B and F. F from B. C and G, we subtract G from C. And then D and H, we subtract D from H. I know, super easy, okay? So let's take a look at an example. In this case, it asks us to subtract these two matrices, but you notice we can't subtract these two matrices because they have different dimensions. This matrix has 2 rows and 2 columns, so it's a 2 by 2. And this matrix has how many rows? 2 rows, and it only has 1 column. Okay? So in this case, because they don't have the same dimensions, we can't do the matrix operation on them. If we look over here, this matrix has 3 rows and 2 columns, so it's a 3 by 2. Whereas this matrix also has 3 rows and 2 columns, so that's another 3 by 2. So that means we can do the matrix operation. And very quickly, when we do that, we get an answer that looks like this, and some finalized to this. Super easy, okay? And the only reason we could add them is because they have the same dimensions. Okay, moving on. If you need to take a look, you can pause the video. Let's go over here for example 2. Now let's multiply a matrix by a scalar. If you remember scalar multiplication, it's kind of like a vector multiplying it by a number. So that scalar is a number. So for this example, we're going to multiply 3 by this matrix. Or we're going to multiply this matrix by 3, which means we're going to multiply 3 by each element in the matrix. 3 times 0, 3 times 2, 3 times negative 7, 3 times negative 1, 3 times 6, 3 times 4. And the resulting matrix is this. Okay? Take a look over here. Still, it doesn't matter about the dimensions of the matrix. We're doing scalar multiplication, so we're multiplying negative 2 by every entry in the matrix. Okay? And we have something that results in looking like this because we're doing multiplication. I know you guys are saying, when is it going to be difficult? Well, it is going to be a little bit challenging. And so let's go to that, when it will be challenging. Before it gets to challenging, I want to review this. Matrices are kind of, since they're made up of nothing but numbers, they hold the same properties as numbers. So we have the associative property. And in this case, A, B, and C are not numbers, but they're matrices. So you can only add 2 matrices at a time, just like you can only add 2 numbers at a time, but it doesn't matter the order. So I can add A and B together and then add C to their resulting matrix, or I can add B and C together and add it to A, and it'll be the same matrix. Community property, since it's A plus B, it doesn't matter if we add B plus A. Scalar multiplication works the same way as vector distribution. K times A is the same, plus K times B is the same thing as K times A plus B. In this case, again, K is the scalar. And it works also for the distributive property as well. So let's talk about, what if I want to take, instead of adding or subtracting 2 matrices together, what happens if I want to multiply 2 matrices together? So in order to multiply matrices together, they don't have to have the exact same dimensions, but something does have to match. So if I want to multiply the matrix A and B together, then the number of rows that the first matrix has, the number of columns that the first matrix has to match the number of rows that the second matrix has. So in other words, these 2 numbers must match. M and Q don't have to match, but N and P have to match. The number of columns in the first matrix has to match the number of rows in the second matrix. And if they do match, then when you multiply the 2 matrices together, you're going to get another matrix that has the dimensions as the same number of rows as the first matrix and the same number of columns as the second matrix. Okay? And so we're going to take a look at an example. And how you do that is a little bit trickier than the rest. Doesn't mean it's different. Now here are the words to how you describe it to multiply the matrix. Ith row of A, jth column of B. But to me, it helps to describe what's going on. So if I want to figure out this position, which is the first row and the first column of the resulting matrix, then what I have to do is I have to multiply. In order to get this answer, I have to multiply the first row of the first matrix times the first column of the second matrix. But it's not multiplying row by column. I'm multiplying entries and taking the result of the product. And I know that may sound difficult, but let's take a look at what we're doing. A, first times first, is A times E. And then second times second is B times G. And then we add up the resulting products. Okay? That's the process. To figure out the next term in the matrix, in this case, this is the second row, but the first column. So I use the second row of the first matrix times the first column of the second matrix, because this is the second row and the second column. So this one was the first row, first column. This one is the second row, first column. And that's why we use the second row and the first column. So in other words here, first times first, C times E, second times second, D times G. And then I add the 2 together. We do the exact same process for each of the other ones. So over here, I do the same thing if I want to figure out, in this case, this is the second row this is the first row, sorry, second column. So that must mean I'm going to use the first row. So that's the first row, and I'm going to use the second column. Then first times first, A times F, and B times H. And that's what I do that here. And then for the last one over here, second row, second column, do the exact same process, but in this case we're using the second row of the first column and the second row of the second row of the first matrix and second row of the second column. So first times first, C times F, and D times H. Okay? The associative property of multiplication doesn't matter which two matrices you multiply first by. Same as well here, doesn't matter which two, but A times B and A times C, and then you add them together. And the same works for the other direction as well. Again, only if these matrices can be multiplied together. In other words, the number of columns in the first number of columns in the first matrix is the same as the number of rows in the second matrix. And this is for scalar multiplication. Doesn't matter which one you do as well. So this video is a little bit longer, but that's because I wanted to show you step by step. And you can of course look up how to do some matrix multiplication. Let me show you some examples. So here's multiplying A times B. An order does matter for the matrix. That gives you the particular results. And here's another example where A, B, and C, in this case, we can add A and B together and multiply it by C, because the number of columns in A and B is 2, and the number of rows in C is 2. So that's why we can multiply these together, and these are the resulting matrices. Okay. All right. Sorry the video is too long, but hope you'll enjoy.